Hello everyone, I'm Zifan Xie, a PhD student from Huazhong University of Science and Technology. Today, I will present our paper, How does code optimization impact the third-party library detection for Android applications?
We're looking into vulnerabilities in open-source third-party libraries which may affect closed-source applications. In fact, 60% of Android app code comes from libraries on average, potentially affecting known vulnerabilities. Our research problem is to check whether a given Android app is affected by these known vulnerabilities. Existing solutions include library version detection approaches, which examines the version of the libraries encapsulated in the app and reports vulnerabilities by querying the NVD. They will generate a warning for each vulnerability contained in the app. Examples include tools like LibScan and ATB Hunter. While these tools can identify libraries and their vulnerabilities to some extent, they often generate high false positive rates due to code transformations. Let's look at D8 and R8, which are embedded in the Android SDK and serve as the default compilers for Android apps. D8 was developed to handle JVM to ART bytecode conversion, while R8 extends these capabilities by adding advanced features for code shrinking, obfuscation, and optimization. The supported strategies are shown in the table. These transformations will significantly alter the code structure. For code obfuscation, R8 will enable identifier renaming and package flattening. In this example, the app's original hierarchical structure is disrupted with all class names, function names, and variable names renamed. It's worth noting that the challenge of obfuscation has been extensively discussed in existing research like LibScan. For code optimization, R8 applies various strategies to improve execution efficiency. In this example, R8 enables inlining, which replaces the function call with the body of the callees. However, existing research has overlooked that code optimization can impact library detection, motivating us to examine its effects on detection tool performance. To evaluate existing approaches, we assembled a dataset of 20347 open source apps and randomly selected 200 of them for compiling. These apps contain 31 libraries with known vulnerabilities. Dataset 1 includes 200 apps compiled with 5 configurations, D8 only, obfuscation, shrinking, optimization plus shrinking, and R8's default setup with all features enabled. Dataset 2 consists of 50 apps, each subjected to 13 individual optimization strategies, allowing us to examine the impact of each specific optimization on library detection. We selected 4 state-of-the-art library version detection tools: LibScan, LibScout, LibPacker, and LibID. For performance evaluation, we measured the F1 score at both the library and version levels. We first examined the pervasiveness of R8 across Android apps. In our analysis of 247 apps, we found that 58.8% use only D8, while 41% rely on R8. This observation prompts us to conduct a systematic analysis of how code optimization affects the effectiveness of library detection tools. Our second research question examines the impact of code optimization on library detection using dataset 1, where each app is compiled with 5 configurations. The table shows the results, revealing that R8's default strategy poses significant challenges. For example, LibScan's F1 score drops to 41.1% at the library level and 14.7% at the version level. This highlights the limitations of current tools in handling optimized and obfuscated code, emphasizing the need for more robust detection solutions. Our third research question examines how different optimization strategies affect library detection using dataset 2, where each app is compiled with 13 distinct strategies. The graph shows F1 scores for LibScan at both the library and version levels, with the red dashed line indicating the worst case scenario and the red solid line showing the best case. Notably, inlining and call site optimization have the most impact, resulting in low F1 scores and significantly reducing LibScan's effectiveness. This highlights the need for detection tools that can better handle these two impactful optimization techniques. To understand code optimizations better, let's focus on two impactful strategies: call site optimization and inlining. First, call site optimization. It removes unused parameters and return values, altering the function's prototype. For instance, redundant or constant assigned parameters are removed, making the function prototype simpler. Next, inlining. This strategy replaces a function call with the actual body of the callee based on specific key heuristics. For example, if a callee is only called twice and its size is less than 28, it can be inlined at the call site. Our key observation is that through fine-grained static analysis, we can approximate and address the challenges from these optimizations. For call site optimization, we can track these unused parameters or return values in library methods. This helps us infer the prototype of an optimized method. As for inlining, we can follow the inlining process to understand how library methods are synthesized into app methods. We introduce LibHunter to detect library versions effectively, even against challenges from code optimization, obfuscation, and shrinking. LibHunter takes an Android app and candidates libraries with all versions as inputs and outputs all detected library versions within the app. LibHunter begins with preprocessing, where it extracts key features and constructs a call graph. Here, we integrate Insight 1 for call site optimization, which allows us to track unused parameters and return values. Then LibHunter attempts to the matching between libraries and the app. There are 3 steps. Step 1 is signature-based class matching. It matches classes based on signature patterns. Step 2 is similarity-based method matching. It identifies partial matches between methods. Step 3 is cross-inlining method matching. We apply Insight 2 for inlining here, thus predicting how the library methods are synthesized into app methods. Due to time limit, we mainly explain how we integrate the two insights. To tackle challenges from code obfuscation and optimization, we employ transformation-resilient features through a method fuzzy signature. For example, suppose there is a method with the prototype fun int p1 long p2. Existing methods represent its fuzzy signature as int long. This signature is to match functions between the app and library because it can mitigate the challenge from identifier renaming. However, this signature is unstable as CSASO can alter the function prototype. Our approach tracks parameters and the return value usage across all call sites of the callee. Step 1 is to track if a parameter is constant, unused, or if the return value is discarded. At step 2, suppose return value and P2 are marked unused. We rewrite the signature as a regular pattern. This rule can be used to perform method signature matching and mitigate the impact of call site optimization. To address the challenges posed by inlining, we focus on understanding how library methods are synthesized into app methods. Our approach involves two key steps. Step 1 is method synthesis. For each function call in the library method, we determine if it should be appended to the call chain. This process is iterative because each callee may also inline its own callees. This helps us create a synthesized version that includes the full call chain. Step 2 is function similarity calculation. We then compare this synthesized method with the API method by examining opcodes and strings to assess similarity. Due to time limit, for more details, please refer to the paper. In our evaluation, we compared LibHunter with existing tools across different compilation configurations on dataset 1. Even in challenging scenarios with obfuscation, optimization, and shrinking, LibHunter achieved the highest F1 scores, outperforming baseline tools by 29.3% at the library level and 36.1% at the version level. LibHunter demonstrated resilience against various optimization strategies. For instance, at the library level, it outperformed LibScan by 36.1% for call site optimization and 40.8% for inlining. These results confirmed that our approach effectively adapts to different optimizations, improving detection accuracy. To validate LibHunter's usefulness, we collected 10,000 popular Google apps using 31 vulnerable libraries as candidate libraries. LibHunter will report a warning if the tool detects a vulnerable library version. The results show that LibHunter identified 36,761 vulnerable library versions in these real-world apps than other tools due to its robust resistance to code optimization. In conclusion, our study is the first to focus on detecting library versions in optimized Android apps. The evaluation results demonstrate that LibHunter performs exceptionally well across various datasets and optimization strategies. Additionally, LibHunter has proven effective in real-world scenarios. Thank you for listening.